In the late 1930s and early 1940s, several advanced nations around the world were hard at work developing completely new rocket engines for aviation. Among them, Germany advanced further than most. While several other countries, including the Soviet Union, remained largely at the stage of experimental prototypes, German engineers brought a rocket-powered interceptor through development and into limited combat use. The Me-163 holds a unique place in aviation history. It became the only tailless aircraft with a liquid-propellant rocket engine not only to complete flight testing, but also to enter service and see combat. It was also a highly specialized machine, a daytime interceptor designed primarily to attack Allied heavy bombers. To do that job, it relied on very high speed for its era and an exceptionally rapid climb. The aircraft's designation, Me-163, was also somewhat misleading. Willy Messerschmitt and his company played only a limited role in the original concept, and by the naming conventions of the time, the aircraft more logically would have carried the name of its chief designer, Professor Alexander Lippisch. Two officials from the German Aviation Ministry also played an important role in moving the project forward. Dr. Adolf Baumker, head of the testing department and a supporter of rocket aviation, and his deputy, Dr. Hans Lorenz. Lorenz was the one who proposed combining a rocket engine with a tailless airframe so that the aircraft's critical structures would be kept as far as possible from the exhaust. Later developments showed that this engineering choice was well-founded. That was how Project X began, a major effort to design and build a rocket interceptor. At first, Professor Alexander Lippisch and his team of engineers worked at small glider manufacturing plants. However, due to a lack of production capacity in late 1938, the entire group was transferred to the massive Messerschmitt factories in Augsburg. There, a special department was set up for them, consisting of Lippisch himself and 12 of his best staff members. This meant the ambitious Project X officially fell under Messerschmitt's management, and the future aircraft received the Me-163 designation. Though it's worth noting that the local factory workers treated this outside project coolly and with outright suspicion. In fact, the first German rocket plane wasn't the Me-163 at all. It was an experimental aircraft built by the rival Heinkel company, the HE-176. Its initial tests, which took place in the summer of 1939, had a major effect on the fate of Project X. The problem was that the powered flight lasted for only 50 seconds, and the top speed was a modest 217 miles per hour. At the time, experts came to a disappointing conclusion. Rocket aircraft burned through large amounts of fuel, and their time in the air was critically short. After that, the German High Command's interest in developing rocket aviation noticeably cooled off, which nearly killed the entire program moving forward. But these setbacks didn't shake the confidence of the team at Department L. With plenty of experience building tailless aircraft under their belts, they pressed on. During extensive wind tunnel testing of scale models, the engineers caught a crucial detail. The special end plates on the wingtips sometimes triggered a dangerous flutter. Rather than risk it, the designers opted for a more conservative solution, a conventional vertical fin on the fuselage. To keep the airplane as stable as possible in the air, both the leading and trailing edges of the wing were given a sharper angle, creating a pronounced swept-back design. Taking all this new data into account, the dedicated team began designing a new aircraft, dubbed the DFS-194. Its design was so well thought out and versatile that it allowed for the relatively easy replacement of a conventional piston engine and tail propeller with a real rocket engine. And they could do this without needing major modifications to the airframe itself. Because of the extreme secrecy surrounding the program, chief designer Alexander Lippisch was not even allowed to see the engine blueprints. He only knew its general dimensions, mounting points, center of gravity, and the basic system requirements given by the engine developers. By late 1939, this unique DFS-194 was completely assembled. In early 1940, it was secretly shipped off to the Peenemünde Research Center, later known for testing the V rockets. First, the aircraft made a few cautious unpowered glide flights while being towed. Once they were sure the aerodynamics worked as intended, they installed a liquid-propellant rocket engine designed by Helmuth Walter, the RI-203. The exact same engine was used on the HE-176 aircraft, but for this new airplane, its thrust was intentionally dialed back. With this change, they managed to extend the engine's continuous burn time to 150 seconds. This power plant used what was known as a cold cycle. The core of the process was that hydrogen peroxide rapidly decomposed when it hit a special catalyst, sodium permanganate, releasing a large amount of heat. The gas produced by this chemical reaction blasted out of the nozzle with incredible force, generating almost 880 pounds of thrust. In the summer of 1940, full-scale test flights under rocket power finally began. As expected with a completely new aircraft, there were a few minor technical issues. However, these tests showed that the airplane responded well to the controls, remained stable in the air, and most importantly, had a very strong climb rate. For a future fighter interceptor, this was a critical feature. In level flight, the aircraft reached 341 miles per hour. These results drew renewed attention from the aviation ministry, which again took a serious interest in the project. The experience gained during these tests allowed the engineers to move directly into developing the pre-production aircraft. At first, they carried some fairly complicated working designations, but before long, the new airplane was soon renamed the Me-163. This was despite the fact that over at the Messerschmitt plant, a very similar designation, the Bf-163, was already assigned to a completely different light aircraft. At the same time, the German High Command was doing everything it could to throw off foreign spies. To do this, they deliberately scrambled the serial numbers on the first Me-163 prototypes, assigning them random index numbers to create the illusion of a massive fleet of existing aircraft and completely cover up the true story of their development. This upgraded prototype made its initial flights under tow behind a powerful twin-engine Me-110 fighter. They had to move the testing to the larger Lechfeld airfield since the company's home base in Augsburg was too cramped for these high-speed maneuvers, but when it came to landing, the engineers hit a serious snag. The touchdown speed was incredibly high, and since the airplane completely lacked brakes or landing flaps, it regularly rolled right off the end of the runway. This often led to severe damage to the aircraft. In fact, the same problem destroyed one of the prototypes during a transfer flight to another base. As the aircraft designer Alexander Lippisch himself later recounted, his main goal while developing the Me-163A was pushing for the absolute highest speed possible. He claimed the project was meant strictly for scientific research, not for building a combat aircraft. Still, he made these claims in the 1960s, 2 decades after the end of World War II. From that perspective, that explanation is open to question. It is hard to imagine the High Command committing that level of funding without seeing clear military potential. In design terms, the Me-163A was overall very similar to its predecessor, the experimental DFS-194 glider. However, the engineers significantly cleaned up the aerodynamics. The fuselage got smoother lines, the glass cockpit canopy was more rounded, and they noticeably enlarged the tail section for better control. The takeoff and landing sequence was highly unconventional. The airplane accelerated for takeoff on a heavy-wheeled dolly, which it jettisoned immediately after liftoff, and it landed on a retractable skid. The aircraft featured wooden wings with one unusual aerodynamic feature: a variable sweep angle along the leading edge. Up to about the midspan, the sweep was 26 degrees, but closer to the wingtips, it increased to 31 degrees. To make sure the airplane flew stable and kept its balance, the designers used some unique airfoil profiles that Alexander Lippisch had personally developed. Beyond that, the wing had a complex twisted geometry, and they fitted it with special air brakes to safely bleed off speed before touchdown. It is also worth noting that beyond refining the aircraft's external lines, the engineering team patented roughly 50 new inventions, most of them related to flight control mechanisms. Even without counting the completely new engine type, that level of innovation shows how ambitious the project was and how much technical risk its designers were prepared to accept. Meanwhile, the unpowered glide tests pushed forward. Thanks to the data they gathered, the engineers were able to fine-tune the balancing on the rudder and elevons. After those tweaks, they did not run into any more dangerous situations in the air. The successful high-speed dive tests finally proved that the fundamental design of the airplane was sound. This strengthened the leadership's confidence that the project was worth pursuing. Work on the highly classified project began to speed up noticeably. A big part of that was the personal backing of Ernst Udet, the Inspector General of Aviation. He had actually shown up to a few of the tests and saw the aircraft's potential firsthand. By the summer of 1941, The engineering team had built 5 prototypes. They shipped 2 of them off to the secret base at Peenemünde. Once there, they fitted them with new rocket motors that featured variable, stepped thrust control ranging from 330 to 1,650 pounds of thrust. The internal tanks held around 2,645 pounds of highly specialized rocket fuel. Flying at full throttle, that fuel supply would only last for a mere 2.25 minutes. Fully loaded, the overall takeoff weight of the aircraft came out to over 4,850 pounds. The first full takeoff under its own power took place on August 10, 1941. Just a few days later, on August 13th, the aircraft broke the 497 miles per hour mark. At the time, that was well beyond the official world speed record. The absolute best result they could manage taking off from the ground was 571 miles per hour. Going any faster just wasn't possible due to the limited fuel supply, since the entire flight lasted only about 4 minutes. To try to reach 621 miles per hour, test pilot Heini Dittmar came up with an ambitious plan. He decided to have the fully fueled aircraft towed up to an altitude of about 13,000 feet and only fire up the rocket engine after detaching. They put this idea into practice on October 2, 1941. An Me-110 heavy fighter towed the experimental Me-163 up to 13,000 feet, and then they dropped the tow cable. Dittmar fired the engine and the airplane rapidly accelerated to Mach 0.84. Instruments on the ground clocked it at almost 624 miles per hour. But at that speed, the aircraft suddenly began vibrating violently and abruptly dropped its nose, plunging into an uncontrollable dive. This forced Dittmar to shut down the engine immediately. As soon as the airplane slowed down and bled off some speed, he got his flight controls back. The Me-163 managed to land successfully, though its metal skin was heavily warped from the massive stress. Despite the near-fatal ending, this flight remained the peak performance achieved by this model. After carefully analyzing the incident and running some extra tests in a wind tunnel over in Göttingen, the engineers figured out what went wrong. It turned out that the sudden nose-down pitching was caused by elastic deformation in the wing. At those extreme speeds, the wingtips were twisting under aerodynamic load, which is exactly what dragged the aircraft down. To fix this, they had to completely redesign the wing. They gave it a constant leading edge sweep angle of 26 degrees. And to keep the airflow from separating at the wingtips, they installed special fixed slats on the front. This proved to be an effective fix. The aerodynamic drag barely increased at all, but now it was practically impossible to force the airplane into a deadly spin. That wing design was one of the key reasons for the airplane's performance. Modern aerodynamics suggests that for high subsonic speeds, roughly 497 to 559 miles per hour, a sweep angle between 25 and 30 degrees is highly effective. Lippisch arrived at a configuration in that range while trying to balance a tailless aircraft, and the result proved well suited to transonic flight. As a result, the Me-163 avoided some of the severe aerodynamic problems that affected a number of experimental aircraft of the era, such as major shifts in aerodynamic center and sudden increases in drag. So while the airframe performed well, the rocket engine remained a constant problem. The feed lines for those specialized chemical propellants kept getting clogged, which meant the fuel was entering the combustion chamber unevenly. This caused incredibly dangerous thrust surges mid-flight and sometimes even led to sudden explosions. The designer, Alexander Lippisch, couldn't exactly work smoothly with the engine developers to solve these critical issues. After some serious personal clashes with the head of the company, Willy Messerschmitt, he was forced to leave the firm for good. Lippisch relocated to Vienna, where he successfully set up his research department at the local Aerodynamics Institute. By March 1943, a total of 10 Me-163A rocket aircraft had been built. Much of the organizational credit for this went to Wolfgang Späth, who, starting in April 1942, served as the project director handling the production and acceptance of these aircraft on behalf of the Luftwaffe. Some of these airplanes didn't even have engines, so they were later used as standard gliders for training young pilots. On other airframes, engineers actively tested new aerodynamic solutions like a wing with constant sweep, and they also experimented with the landing skid deployment mechanisms and other vital onboard systems. They tried installing gas rudders on one of the prototypes, but the idea turned out to be a failure and was quickly scrapped. Experiments with other engine types didn't bring the desired success either. One unusual episode involved an ME-163A armed with 24 R4M unguided rockets. This wasn't an official order from high command, but rather the personal initiative of the commander of a training unit based at the Uddetfeld airfield, which trained pilots. In October 1944, this enterprising commander simply borrowed 2 rocket launchers and a whole crate of rockets from a neighboring squadron that flew the Me-262 jets. After that, together with his mechanics, he installed this arsenal on his airplane. The launcher itself was very simple. It was just a set of standard wooden rails attached to the underside of the wing. They placed 12 rockets under each wing. The R4M rocket was an unguided projectile with a 55mm caliber. It was about 32 inches long, and its launch weight was 8.5 pounds. The explosive charge itself weighed a little over 1 pound. This rocket used folding fins that were held in place before launch by simple paper sleeves. When fired, the paper instantly tore away, and the fins deployed under the pressure of the oncoming airflow. The idea was clever, but these rockets never became the official armament for the Me-163 interceptors. Leadership simply didn't have the time or available specialists to bring this field improvisation into mass production. Initially, they wanted to name the new combat version of the aircraft the Li-163S, but later decided to go back to the familiar Me-163 designation. Even though the Me-163B combat model and the Me-163A trainer looked almost identical on the outside, their internal design differed drastically. At the center of the combat aircraft was a new rocket engine designed by Helmuth Walter, which operated on a so-called hot cycle. The main advantage of this engine was the ability to flexibly adjust the thrust anywhere from 220 to 3,300 pounds. The engine's creator claimed that at maximum power, it would consume between 5.5 and just over 6.5 pounds of fuel per second. Based on these calculations, the aircraft's chief designer, Alexander Lippisch, designed the Interceptor so that there would be exactly enough fuel for 12 minutes of active flight. The plan went like this: 3 minutes of engine operation at full thrust for a sharp takeoff and rapid climb, with the remaining 9 minutes at reduced power for attacking enemy bombers and returning to base. But harsh reality quickly made its own adjustments. In practice, the engine burned much more fuel than expected. This caused a massive number of problems both during testing and in the Interceptor's subsequent combat use. While designing this aircraft, engineers had to solve a difficult problem: how to maintain the proper balance of the airplane in the air when it was rapidly losing weight due to burning huge amounts of fuel and firing off ammunition. So that the center of gravity wouldn't shift, the main oxidizer tank, which held a massive 275 gallons, was placed right in the middle of the fuselage. To maintain perfect balance as the oxidizer was depleted, 2 additional 16-gallon tanks were moved forward and mounted right inside the cockpit on either side of the pilot. At the same time, they placed the entire fuel supply in the wings. By spreading it across the wingspan instead of along the fuselage, the aircraft remained more stable as it burned through the mixture. Each wing held 2 tanks, a 19-gallon one and a larger 47-gallon one. Since these rocket fuel components were incredibly aggressive and dangerous chemicals, storing them in standard tanks just wasn't an option. For example, pure aluminum was well suited to hydrogen peroxide, so that's what they welded those tanks out of. But for the fuel itself, glass was actually the best material. Obviously, sticking a massive glass tank inside an airplane is a terrible idea because it's so fragile. So the engineers came up with a clever workaround. They took sturdy steel tanks and coated the insides with a special glass enamel. They used this exact same complex process for all the fuel lines inside the aircraft. The fuselage had an elongated spindle-like shape, with special fairings on the top and bottom that gave it an oval cross-section. To make maintenance easier, ground crews could quickly split the fuselage in half for full access to the engine. Up front, the nose section was made of lightweight duralumin and housed the equipment bay, the cockpit, an oxidizer tank, and a special landing skid. This whole assembly rested on a heavy-duty lower beam and a few supporting rings. These rings pulled double duty. One acted as the front wall of the cockpit and held up the heavy armored nose, while another served as a solid firewall between the pilot and the fuel tanks. The wings, the pilot's armor plates, and the engine itself were all bolted right to these supporting elements. On top of that, the outer skin of the nose section was stressed, carrying part of the load and making the airplane even stronger. The very tip of the nose was a cone cast from armored steel about 0.6 of an inch thick. From an engineering standpoint, this solution had a clear purpose. Although a metal cone weighed more than a standard flat armor plate, its shape improved the chances that bullets and shell fragments would glance off rather than strike squarely. That, in turn, increased the pilot's protection. Immediately behind this armored cone sat the most critical avionics and equipment. Just aft of the equipment bay was the cockpit, which was relatively roomy for such a small fighter. It was enclosed by a transparent canopy that hinged open to the right. Interestingly, this canopy was a single, continuous piece without any metal framing, yet it easily handled the immense pressure of flying at very high speeds. Decades later in the 1960s, creating these frameless canopies without visual distortion would later be treated as a major advance in aviation. Over time, the designers added a small vent window to the canopy because the toxic oxidizer fumes kept burning the pilot's eyes. Up front, the pilot had the extra protection of a thick 3.5-inch piece of bulletproof glass sitting right above the instrument panel. But on either side of the cockpit, engineers placed 2 protected oxidizer tanks, each holding about 16 gallons. This was a dangerous but necessary compromise. The designers had to maintain the aircraft's center of gravity as it burned through fuel. There was a notorious incident in which one of these tanks cracked during a hard landing and the leaking oxidizer fatally injured the pilot. In all future designs, they made sure to keep the tanks out of the cockpit. Behind the pilot was a firewall backed by 3 armor plates. A 1/2 inch of steel protected the head and back, while roughly 0.3 of an inch of armor covered the shoulders. The seat itself was mounted right to this wall on special spring shock absorbers. The cockpit itself wasn't pressurized. Because of this, pilots constantly suffered from the bitter cold at altitude, and the incredibly fast climb rate meant they had to be in peak physical condition just to handle the extreme pressure changes. Tucked right behind the cockpit was the main oxidizer tank, which held a massive 275 gallons of fluid. To make it easier for mechanics to install this huge tank and work on the fuel lines, the entire top of this bay was covered by a removable panel. The filler necks for refueling were right up there on top too. Along the bottom of the forward half of the fuselage ran a heavy beam, and the landing skid was securely attached right to it. The tail section of the airplane was constantly exposed to extreme heat from the engine, so both its internal frame and outer skin had to be made from heat-resistant steel. A wooden vertical stabilizer was mounted on top of this section. Attached to it was the rudder, which featured a lightweight duralumin frame covered in heavy-duty fabric. The engineers carefully tuned this rudder, giving it perfect aerodynamic and weight balance. Down below the tail section, they mounted an extra ventral fin that held a tiny tailwheel, which could retract into the fuselage during flight. On top of that, they cut special ventilation slots all over the tail bay. These helped cool down the scorching engine and quickly blew out any dangerous fuel vapors. The takeoff and landing gear on this aircraft was unusual. It consisted of a steel landing skid, a small tail wheel, and a special takeoff dolly that was jettisoned right after lifting off. At first, the engineers experimented with materials, trying to make the skid out of wood or light duralumin, but they ultimately went with stronger steel. The takeoff dolly had wheels measuring about 27.6 by 6.9 inches, and it locked securely onto the skid with a special latch. When the pilot started retracting the skid into the fuselage, this latch automatically released, and the dolly just dropped away since it wasn't needed anymore. A complex pneumo-hydraulic system handled the extension and retraction of both the skid and the tailwheel. Before every flight, the ground crew filled special bottles with compressed air. That energy transferred first to hydraulic accumulators and from there to hydraulic cylinders, which also doubled as shock absorbers to soften the impacts. The rear wheel was very small, measuring just 10.5 by 3.3 inches, and the pilot steered it using a rigid push rod. However, this bizarre landing gear setup drew a ton of criticism from aviation experts. The issue was that if the dolly dropped too early, it could bounce hard off the concrete runway and strike the airplane. We know that at least one Me-163 fighter crashed due to this exact fatal design flaw. Things got even worse if the mechanism jammed and the dolly didn't release at all. When that happened, landing the aircraft safely was virtually impossible. To make matters worse, the system only stored enough energy for a maximum of 1 or 2 gear cycles. If the mechanism totally failed to work, the pilot had only one choice: bail out and abandon the fighter. On top of that, the shock absorption on the skid itself was incredibly weak. During hard landings, this often left pilots with severe spinal injuries. Any engineer looking at the blueprints would instantly realize that the chosen setup just couldn't handle heavy vertical impacts with the ground. Because of this massive flaw, the designers actually had to mount heavy-duty shock absorbers straight onto the pilot's seat. The track width between the dolly's wheels was also too narrow, which meant the airplane constantly wobbled and lost directional stability during the takeoff roll. And once the flight was over and the airplane landed on its skid, you couldn't just tow it off the runway like a normal aircraft. The ground crew had to bring out a dedicated transport trailer, jack the aircraft up, and haul it away from the landing spot that way. So why did the engineers make such sacrifices? All of these numerous drawbacks came down to one main reason: the designers were trying to remove as much weight from the aircraft as possible, sacrificing comfort and safety in the process. This aircraft's wing was made entirely out of wood. Its sweep was 26 degrees along the leading edge and 9 degrees along the trailing edge. To make sure the airplane held steady in the air and was as stable as possible, the engineers gave the wing a special shape that smoothly tapered from the root to the tips. The entire trailing edge of the wing was taken up by flight controls. The elevons were positioned closer to the wingtips, while the trim flaps were located closer to the fuselage. The elevons could deflect 31 degrees both up and down, allowing the pilot to easily control the aircraft's roll and pitch. The trim flaps, however, worked a bit differently. They didn't move independently of each other and were strictly responsible for the aircraft's longitudinal balance in flight, deflecting 9 degrees up and 12 degrees down. Both the elevons and the trim flaps featured a lightweight wooden frame securely covered with aviation-grade fabric. To keep the airflow smooth over the wing and prevent the aircraft from losing control, a fixed slat was installed at about mid-span. And to make sure the airplane wouldn't need an overly long runway, the designers added landing flaps. These were made of a sturdy aluminum alloy and were deployed using hydraulics, which the pilot had to pump with a standard hand pump right there in the cockpit. A large wooden spar served as the main structural support for the wing. The engineers routed the rigid control rods through it, which freed up additional space in the wing for fuel. They placed 2 tanks in each wing. The front one held about 19 gallons of a special mixture, while the rear one held almost 47 gallons. The skin was additionally reinforced in the areas where these tanks were located. The outer skin itself was made of high-quality beechwood veneer securely glued together. The onboard equipment and aircraft systems had a few quirks as well. For example, extending and retracting the landing skid, as well as the tail wheel, was powered by a hydraulic system that doubled as a shock absorber. The takeoff dolly would automatically drop away the exact moment the pilot started retracting the skid. The system ran on compressed air, which had to be pumped in before every combat sortie. This air was stored in cylinders hidden in the nose and under the fuselage. Plus, compressed air was used to reload the cannons. For this, separate small cylinders were placed right next to the weapons. The electrical system was arranged in a practical way. It consisted of a 24-volt battery and a powerful 2,000-watt generator, which was spun by the incoming airflow using a small windmill. The battery only provided power while the airplane was on the ground and during the takeoff run. But as soon as the aircraft picked up enough speed, all the instruments switched over to being powered by the wind-driven generator. This solution saved a lot of weight, since dragging along a massive battery meant to last the entire flight would have been way too heavy. Since the airplane was meant to fly at high altitudes where oxygen becomes scarce, the designers made sure to provide for the pilot's survival. A special oxygen unit was installed on the right side of the cockpit. The oxygen cylinder itself, along with its filler valve, was mounted under the right side of the wing. For communication, they used an FUG-16ZU radio set, which was paired with a friend or foe identification system model FUG-25A. The equipment blocks were placed in the cockpit and the forward compartment, while the antennas were scattered all over the aircraft. One was mounted on a mast on top of the fuselage, another was built into the tail section, and one more was hidden under the right wing. Some examples were additionally equipped with a radio compass. In practice, that modification may have been unnecessary. The reason was simple. This aircraft was used strictly during the daytime, and its flight range was so short that getting lost in the sky under these conditions would have been difficult. As for the flight and navigation instruments, there was nothing exotic here. The panel looked just like the ones in most standard airplanes of the time. Right in front of the pilot were a compass, an artificial horizon, airspeed, altitude, and rate of climb indicators, along with an onboard clock. The power plant status was monitored through separate indicators. They showed how much fuel was left, the rotational speed of the turbopump, and the thrust level the engine was putting out. The armament on the first production units of the Me-163B0 fighter, which they started installing in early 1943, consisted of two Mauser MG-151 cannons. Their caliber was 20 millimeters, and the ammo loadout came to 100 rounds per gun. Starting with the 47th aircraft produced, engineers decided to beef up the firepower. Now they were fitting the fighters with two more powerful Rheinmetall Borsig Mk-108 cannons with a caliber of 30 millimeters. The updated variant was designated the Me-163B1. However, because of the larger caliber, the ammo capacity had to be reduced to 60 rounds per cannon. These cannons were mounted right at the wing roots, the ammunition belts neatly wrapped around the oxidizer tank, and were positioned perfectly at the aircraft's center of gravity. This was a practical engineering solution. As ammunition was expended, the aircraft's balance changed as little as possible. For aiming, they used a special Revi reflector sight, securely protected by armored glass above the instrument panel. But even this setup drew heavy criticism from the experts. The main problem was that the Mk-108 cannons were not especially impressive in either rate of fire or reliability. On average, there was roughly one system failure for every 100 shots fired. Considering that an aerial attack at breakneck speeds lasted only a matter of seconds, the number of rounds fired might simply not be enough to guarantee the destruction of a heavy enemy bomber, and the pilot just didn't have the time to try and clear a jam or reload. In an effort to solve the firepower problem, the designers tried to create something entirely new, an SG-500 system called the Jägerfaust. It was developed based on the well-known anti-tank Faust Patrone. It was a rocket-propelled grenade with a caliber of about 50 millimeters housed in a lightweight tubular launcher. 5 of these launchers were mounted vertically at the root of each wing. The concept was unusual. The Interceptor would fly right under the enemy bomber at very high speed, at a distance of 65 to 295 feet. The pilot wouldn't even have to pull the trigger. The rockets were supposed to fire automatically using a sensitive photocell. It would react to the shadow cast by the enemy aircraft overhead. At first, they cautiously tested this technology on the FW-190 fighter, using regular balloons instead of real targets. During one of these training flights, they managed to score an impressive 7 direct hits. Encouraged by this success, the developers decided to integrate the Jägerfaust into the Me-163B0. The first experimental flight with the new weapon took place on December 24, 1944. This time, the target was a large barrage balloon strung between 2 high masts right on the edge of the airfield. Since the tests were taking place at low altitude, the tanks of the Me-163 were only half filled. After a successful takeoff and climbing to an altitude of almost 980 feet, the pilot prepared for the attack and removed the safeties from the photocells. Then something unexpected happened. At that exact moment, an unauthorized salvo of rockets fired off. The powerful blast seriously damaged the canopy glass and even ripped the protective helmet right off the surprised pilot's head. The pilot had to make an immediate emergency landing, during which the aircraft bounced hard several times on the runway. When experts started investigating the incident, they reached an ironic conclusion. The photocells simply reacted to the shadows of ordinary clouds drifting over the fighter. Eventually, they improved the system and installed this innovative weaponry on 12 aircraft. However, it was only used once in actual combat. Even though some sources claim that the Jägerfaust managed to shoot down an American B-17 bomber, those claims remain doubtful. There was another, even more exotic weapon variant being developed in the city of Augsburg in the fall of 1944. On one of the experimental aircraft, the leading edge of the wing was specially reinforced with heavy-duty steel plates. The goal was extraordinary: to use the aircraft for deliberate aerial ramming attacks. The engineers figured the Interceptor could literally slice through the tail section of an enemy bomber without actually damaging itself. They even ran a series of test flights with this modification, but this flying blade never saw real combat action. The aircraft's most distinctive feature was still its power plant. The airplane had 3 oxidizer tanks with a total capacity of over 306 gallons. About 32 gallons were located right in the cockpit, and another 275 gallons in the fuselage. The fuel itself was distributed across 4 tanks in the wings, a total of just over 132 gallons. Altogether, they poured almost 439 gallons of this dangerous mixture on board, weighing in at over 4,460 pounds. Since this substance was extremely explosive, the aircraft were fitted with a special emergency dump valve at the urgent request of the pilots themselves. It allowed them to quickly dump the remaining oxidizer right in mid-flight. This was critical. If the tanks got damaged during a rough landing, the airplane could simply blow to pieces from the slightest spark. The oxidizer, codenamed Mixture T, consisted of 80% hydrogen peroxide. At first glance, it was just an ordinary clear liquid with no color or smell. However, it was mildly toxic. If its fumes leaked into the cramped cockpit, they would instantly make the pilot's eyes water severely. Getting this substance on bare skin was guaranteed to cause severe chemical burns, and contact with certain organic compounds would trigger a massive explosion right on the spot. But the biggest danger of Mixture T was its extreme instability. If the liquid came into contact with even the tiniest speck of a catalyst, like plain old iron oxide, it would start decomposing violently, which often ended in a sudden explosion. By contrast, this stuff dissolved perfectly in water. On the ME-163, it acted as the oxidizer and was also used to generate the steam gas that drove the turbine and pumps. For fuel, they used a different substance, the Mixture C. It was a complex chemical cocktail, 30% hydrazine hydrate, about 58% methanol, and the rest was just plain water. On the outside, it was a colorless, slightly oily liquid with a very sharp, unpleasant ammonia smell. Just like the oxidizer, this fuel was incredibly toxic. It left severe burns on the skin and would instantly explode from the slightest contact with iron oxides. The crucial point came when Mixture C met Mixture T. Together, they formed a rocket propellant that ignited spontaneously without any external spark. A pre-production version of the rocket engine, designated HWK-109509A0, was finally ready in the fall of 1942. It boasted the ability to throttle its thrust anywhere from 661 to 3,307 pounds. This power plant was first installed on the early experimental versions of the ME-163 fighter. However, during test flights, a highly dangerous problem emerged. Sometimes the engine would just suddenly shut down. This happened at the absolute worst times during the transition from a steep climb to level flight, or right after lifting off the runway, just as the aircraft managed to accelerate to 236 miles per hour. These failures led to 2 tragic crashes and several close calls where pilots narrowly escaped death. During a thorough investigation, engineers identified a key detail. Liquid-propellant rocket engines have a specific quirk. If only one of the propellant components builds up in the combustion chamber and then the second one is suddenly introduced, a massive explosion is inevitable. To prevent this, a smart automated system simply killed the engine the moment it detected an interruption in the flow of either liquid. As it turned out, cavitation was occurring in the aircraft's fuel lines, creating dangerous air pockets that triggered the safety system. They managed to successfully fix this issue by heavily upgrading the fuel automation and improving the tank pressurization system. Later on, an improved version of the engine appeared, designated HWK-109509A1. They managed to increase its maximum thrust to 3,527 pounds, while giving the pilot the ability to throttle it all the way down to a minimum of 220 pounds. This specific modification became the beating heart for the ME-163 Komet and BA-349 Natter interceptors. Structurally, this engine, which weighed 370 pounds, consisted of 2 main parts: the accessory section up front and the combustion chamber with the nozzle, which was extended to the rear on a special thrust tube. The main advantage and engineering pride of this system was the use of a specialized turbo pump assembly which seamlessly fed propellant into the combustion chamber. The startup sequence was technically complex. First, the turbo pump shaft was spun up using a standard electric starter. At the same time, the pump fed a small portion of peroxide into the steam generator. There, the liquid hit a solid catalyst and violently decomposed into steam and oxygen. releasing a huge amount of heat. The resulting hot steam and gas blasted against the turbine blades, forcing it to spin even faster. As soon as the system reached the required RPM, the electric starter automatically disengaged. Most of the exhaust gas was dumped through a pipe down the bottom of the fuselage, but a small fraction of it was routed straight into the combustion chamber. This was done to purge the chamber and keep any leftover fuel from pooling inside. This effect is often visible in archival photographs as a light wisp of smoke from the nozzle rather than anything resembling a sustained jet exhaust. When the pilot pushed the throttle forward, the main valves opened up and the engine roared to life with full force, rapidly building power. Fuel was injected into the chamber through 3 separate banks of nozzles, which allowed the pilot to step the power up or down. At top speed, all the nozzles were firing, but when thrust needed to be cut back, 1 or 2 banks would simply shut off. Naturally, just like any other power plant, this rocket engine operated most efficiently right at maximum output. In that mode, the pressure inside the combustion chamber reached 294 pounds per square inch, and the temperature soared to an incredible 3,632 degrees Fahrenheit. But the moment the pilot throttled back, the chamber pressure dropped sharply and fuel consumption per unit of power nearly doubled. So trying to fly slower didn't help save precious fuel at all. This realization ultimately pushed the designers toward a bold idea, creating a fundamentally new dual-chamber rocket engine. If the pilot pulled the throttle back, the engine could be completely shut down right in mid-flight. However, the pump system didn't shut off entirely, it went into a standby mode. It kept up a minimum RPM by using just a small amount of hydrogen peroxide. This engineering solution allowed the engine to be restarted instantly and without any delay whenever it was needed. If a final shutdown was planned, the throttle was moved to a special detent, and the flow of the fuel mixture to the turbine was cut off completely. This power plant had highly sophisticated systems for starting, stopping, throttling, and precisely delivering components in the exact right proportions. On top of that, the engineers included various protection systems and automatic shutoffs for unforeseen situations. The combustion chamber and the exhaust nozzle were continuously cooled by the fuel itself, which flowed back to the pump after circulating through the hot zones. Overall, for its time, it was an incredibly advanced and cutting-edge design. Take the HWK 109509A2 engine, for example. It featured 2 separate combustion chambers. The first one, a powerful primary chamber, produced a maximum output of 3,750 pounds of thrust, which could be gradually throttled down to 440 pounds. The second one, a cruise chamber, operated at a constant 660 pounds of thrust. The developer's logic was simple. The primary chamber fired up during takeoff and steep climbs, while the smaller cruise chamber took over for steady, level cruising. Because of this, the cruise chamber operated at peak efficiency, which drastically saved fuel and significantly improved the aircraft's flight performance. However, this innovative solution came at a price. During level flight, the pump's output was actually overkill, and the massive primary chamber just turned into dead weight. The total weight of this engine was nearly 440 pounds. Initially, this setup was tested on experimental versions of the Me-163B aircraft, and later they planned to install it en masse on the newer Me-163C model. Engineering didn't stand still, and soon the HWK 109509B1 modification appeared. It was a logical evolution of the base version, but now it only had a single combustion chamber. Its thrust could be smoothly adjusted across a wide range, from 440 all the way up to 4,410 pounds. This unit saw heavy use on the Me-163B rocket aircraft and the DFS-345 gliders. Next, the Germans developed the HWK 109509C1 version. This was a dual-chamber variant of the previous engine that put out anywhere from 880 to 4,410 pounds of thrust. It was being prepped specifically for the promising Ju-248 aircraft, which is also known as the Me-263. Overall, by the end of the war, the industry managed to produce around 500 engines in this series, but the high command always liked to have a backup plan. To cut down on technical risks, they contracted BMW to develop an alternative engine called the RLM-109510A. Its main difference came down to the fuel. Instead of the usual oxidizer, it used nitric acid, an incredibly aggressive and highly toxic liquid, while methanol served as the actual fuel. Since this mixture didn't ignite on contact by itself, designers had to throw in a complex ignition system. The trade-off was that pilots could continuously adjust their thrust in flight. They even managed to install this engine on an Me-163, but the refinement process dragged on way too long, and it never saw large-scale use before the war ended. There was also a project for a more powerful dual-chamber, RLM-109-510C engine, putting out anywhere from 1,320 to 5,510 pounds of thrust. They wanted to use it to power the Me-163C Interceptor, but they just ran out of time to get it in working order. Aside from the aircraft itself, the project also stands out for the attention paid to ground operations. Even though the Me-163 was built in relatively small numbers, it required a whole support system. The Germans developed special tractors and dollies to lift and move the fuselage, as well as dedicated refueling vehicles for the hazardous fuel mixtures. Much of this support equipment was mechanized despite the increasing strain on German industry by 1944. Since the fuel components were extremely dangerous and could explode if mixed, ground crews had to be very careful when servicing the Me-163 Interceptor. Their top priority was to make sure all fuel lines and connections were properly sealed. Fortunately, these chemicals dissolved easily in water, so before every refueling, all the funnels, containers, and tools had to be thoroughly washed down. They also thoroughly hosed down the tail section of the aircraft, the combustion chamber, and the engine mechanics. They even soaked the concrete under the fighter and the parking spots for the fuel trucks. Fire crews remained on constant standby, and water was used extensively around the airfield even when no raid was underway. But despite all these safety measures, the fuel remained a constant danger. Aircraft exploded during refueling or takeoff, and others were lost in hard landings after the fuel system failed or ruptured. Ground crews were also exposed to serious risk. In one case, a technician was killed after a fuel component was poured into a container that had not been washed properly after holding another substance. 2 more aircraft exploded on the ramp without a clear immediate cause. In practice, during its early operational life, the Me-163 often posed as much danger to its own crews as it did to Allied aviation. That experience likely strengthened interest in other less hazardous designs such as the Me-262 and HE-162. At first, the DFS plant handled the production of the Me-163, but eventually they decided to shift manufacturing over to the Regensburg facility owned by Messerschmitt. That's where the first 70 pre-production fighters were put together. Gradually, the Germans set up a large production network. This meant that different parts and assemblies for these aircraft were built across dozens of different factories scattered all over Germany. But the final assembly and overall quality control across all the suppliers was handed over to the Klemm Company, whose main plant was located in the Black Forest. The program took a serious hit on August 17, 1943, when American B-17 bombers carried out a heavy raid on the Messerschmitt and Klemm factories. The consequences were severe. The bombs completely destroyed the assembly line for the Bf-109 fighters, and 11 fully completed rocket-powered Komets burned to the ground at the Klemm plant. This devastating raid finally accelerated the process of handing over full control of the project from Messerschmitt to the Klemm Company. From then on, final assembly of the aircraft took place exclusively at the factory in the Black Forest. Components kept coming in from all over. Of course, with such complex logistics, there were bound to be manufacturing issues. During assembly, workers constantly found mismatched parts and minor defects. For instance, engineers had to work hard to get a proper flush fit between the wing and the fuselage. But whatever the case, the specialists ironed out these problems, and the improved second series Me-163 aircraft were finally ready for mass production. On the outside, the new aircraft barely looked any different from their predecessors, except maybe for a change in the shape of the tail vent. On the inside, however, the design was heavily reworked and improved. The logistics process was unusual. After the airplane was put together at the factory, its wings were taken off again. Disassembled like this, it was loaded onto a train and shipped to the Lechfeld airfield. There, the fighter was reassembled, put through a test flight, and only then officially handed over to the Luftwaffe for service. The military received the first production model in May 1944. In June, 3 more aircraft arrived, followed by 12 in July. Production slowly began to rise and hit its peak in December of that year, when the factories rolled out 90 airplanes in a single month. Overall, production lasted until February 1945. During this whole time, Germany managed to turn out 470 Komets, 42 of which were assembled in 1945. Junkers also made an important and growing contribution to the project. The company manufactured 351 wing sets and took part in further development of the aircraft. Based on that work, Junkers engineers created a new variant, the Ju-248, later redesignated the Me-263. German authorities appear to have considered shifting fuller control of the project to Junkers, but the end of the war brought those plans to a halt. The closest Soviet counterpart to the Komet was the By-1 rocket plane. The Soviet Union had its own active research into liquid-propellant rocket engines before the war, although its program developed along a different path and faced several major technical limitations. One of the most important was the lack of specialized turbopumps for a smooth, uninterrupted fuel supply. By 1941, the design bureaus led by Valentin Petrovich Glushko and Leonid Stepanovich Dushkin finally realized that standard piston and rotary pumps just were not cut out for such extreme loads. And at that stage, Soviet engineers had not yet developed effective centrifugal pumps. This serious technical issue left a massive mark on the overall external look and design of the Bi-1 aircraft. The intended combat concept for the Bi-1 closely mirrored the idea behind the German Me-163 Interceptor: a fast takeoff, a steep climb to altitude, one rapid attack on an enemy bomber, and an immediate return to base. Since they didn't have decent turbopumps, Soviet engineers had to use what's called a pressure-fed fuel system. This workaround added a great deal of weight to the power plant. In this area, the Soviet design was at a disadvantage compared with the German one. For the oxidizer, Soviet specialists went with nitric acid, a highly aggressive and toxic liquid. By contrast, the fuel itself was perfectly safe, as it was just regular kerosene. Plus, this mixture didn't ignite on its own when mixed. On paper, this promised some real maintenance advantages compared to their German counterparts. Instead of handling 2 deadly components, ground crews only had to deal with one, which significantly improved fire safety. In fact, constant leaks of corrosive acid mercilessly ate away and ruined the aircraft's structure. The Bi-1 featured a conventional straight wing at the speeds it was intended to reach. This was generally a less favorable aerodynamic choice than the swept wing of the German Me-163. Granted, the landing speed of the Soviet aircraft was noticeably lower, around 89 miles per hour compared to 137 miles per hour for the Germans. And that was despite the Soviet Interceptor having a higher wing loading, almost 61 pounds per square foot versus 46 pounds per square foot for the German airplane. On paper, the raw thrust figures for the 2 engines were in a similar range, although the German power plant offered higher maximum output and appears to have been more reliable. The Soviet D-1A-1100 engine produced between 882 and 2,425 pounds of thrust, burning nearly 12 pounds of fuel per second, with a combustion chamber pressure ranging from 235 to 279 pounds per square inch. The German HWK-109-509A1 engine put out between 220 and 3,527 pounds of thrust, consumed 11 pounds of fuel per second, and had a chamber pressure reaching 294 pounds per square inch. Engine lifespan also differed sharply, about 20 minutes in the Soviet case, versus roughly 2 hours for the German one. It is important, however, to note that the Soviet figures reflect the state of the program in 1942, while the German data comes from the very end of the war. The Soviet short-range Bi-1 Interceptor was almost half the weight of the Komet. It weighed around 3,638 pounds against the German fighter's 8,598 pounds. Thanks to being so light, it boasted a much better thrust-to-weight ratio at takeoff, 0.66 versus 0.41. However, that lower weight came with a major drawback. Powered flight time with full tanks was only about 1.5 minutes, whereas the German aircraft could remain under power for roughly 8 minutes. The Bi-1 made its first flight on May 15, 1942. During its seventh test flight on March 27, 1943, the pilot reached speeds of 466 to 497 miles per hour during a powered run lasting 78 seconds, the program's best result before the fatal crash that ended it. Tragically, it was during this very record-setting flight that the airplane crashed and the test pilot was killed. The main cause of that fatal crash is believed to be that the aerodynamic layout of the BI-1 simply wasn't suited for flying at such extreme speeds, a fundamental flaw the program never had the chance to address. Another important counterpart to the German Me-163B was its Japanese license copy, the J8M1 Shusui, a name usually translated as punishing sword. The story of this aircraft began in the fall of 1943 when the German design was shown to the Japanese military attaché. He considered it promising enough to recommend that Japan acquire a license for the aircraft as part of its air defense effort. In the spring of 1944, the Germans put together all the necessary technical documentation, broke down one Me-163B into parts, and gathered a team of their experts to send to Japan. This cargo, along with the personnel, was loaded onto 2 submarines, but the transfer was only partly successful. Only one of them reached Singapore, and the reference aircraft along with the most important drawings were lost at sea. Even so, Japanese engineers moved ahead with the project. They immediately faced 3 major problems: setting up airframe production from scratch, reproducing the engine, and obtaining the required fuel. Given the shortage of information and the pressure of constant bombing, solving those issues within about a year was a considerable achievement. The submarine arrived in mid-June 1944, and by July 7, 1945, the J8M1 made its first flight for the very first time. Of course, the Japanese punishing sword had some differences from its German ancestor. It was fitted with local cannons, which were longer and heavier than the German ones, and they swapped out the radio for their own. Interestingly, the fuselage of the aircraft was made entirely of metal, and this was during a severe raw material shortage in the country. However, the frames of some control surfaces were still left wooden and covered in fabric. The designers also stripped out some of the equipment and simplified a few systems as much as possible. Thanks to these decisions, the empty weight of the airplane came in at around 3,186 pounds, which actually turned out to be less than the original prototype, which weighed 3,318 pounds. But the biggest headache for the developers was the engine. That was what constantly held things up and put the whole program at risk. The Japanese engineers were plagued by endless equipment failures, unexpected explosions, and test fires. Ultimately, they only managed to get one single engine working right and certified for flight. Even then, it produced about 3,307 pounds of thrust, falling just short of the 3,527 pounds the German original had. And then came the day of the first flight, July 7th, 1945. The aircraft's fuel tanks were only filled halfway for safety reasons. After a sharp takeoff, the Interceptor started climbing rapidly at a 45-degree angle. But at an altitude of about 1,148 feet, the engine suddenly cut out. The pilot tried to make an emergency landing, but it didn't work out. The airplane struck a building at the edge of the airfield with its wing and flipped over. Fortunately, the fuel didn't explode, but the aircraft was completely destroyed, and the test pilot died the next day from severe injuries. During the investigation, they found out that the tragedy was caused by a design flaw in the fuel system. Because of the steep climb angle and the intense G-forces, the remaining fuel just pooled against the back walls of the tanks. The fuel pumps sucked in air instead of fuel, which led to the engine stalling instantly. On that sad note, the story of the ambitious, punishing sword came to an end. There was no time left to fix the mistakes, as World War II was coming to a close. Another, and probably the final counterpart in this story, was the post-war Soviet project known as the I-270. It was based on the German Ju-248, but they decided to significantly simplify its design. During development, Soviet designers again chose a more conventional aerodynamic layout, using a straight wing and a standard tail section rather than adopting a swept configuration for high-speed flight. The I-270 was fitted with the RD-2M3V engine, which in terms of performance was very similar to the German HWK-109509C. It featured a complex twin-chamber design and produced around 3,197 pounds of thrust. At maximum power, this engine could only run for up to 4 minutes, but if the auxiliary combustion chamber was used to save fuel, flight time increased to 8 or 9 minutes. The armament for this interceptor was supposed to consist of 2 powerful, roughly 1-inch cannons. Even with this more conventional aerodynamic layout, the I-270 still reached 621 miles per hour. However, from the very beginning, this project was essentially a research effort. After both built prototypes were lost during testing in 1947, the program was permanently shut down. Among the direct German alternatives to the Me-163, the BA-349A Natter also deserves mention. This unusual aircraft was significantly smaller and consumed much less of that critically scarce fuel. Despite this, its combat radius remained exactly the same as the Komet. The secret was that the Natter took off vertically, just like a rocket, and it didn't need to return to its home base at all after completing a mission. At the same time, the BA-349A was aerodynamically less refined than the Komet, since it also lacked a swept wing. On top of that, operating an interceptor like this required setting up special ground crews. Their job would be to track down and transport the salvaged tail sections of the aircraft, which floated back down on parachutes after the flight was over. But this concept had one massive advantage. Launching the Natter didn't require a proper airfield at all. The launch pad could easily be hidden in the woods or set up practically anywhere convenient. The history of this interceptor started late. Its first vertical launch didn't happen until late February 1945. Because of this, they never managed to officially adopt this unique fighter before the war ended. Another competitor, albeit with some caveats, was the German Enzian surface-to-air guided missile project. Its aerodynamic shape was clearly borrowed from the Me-163B airplane, especially since they were both developed under the roof of the exact same company. As for the power plant, the missile was equipped with 4 solid fuel booster rockets, each producing 3,860 pounds of thrust, alongside the main Walter HWK 109739 liquid-propellant rocket engine. At launch, this missile weighed around 4,340 pounds and carried a massive warhead weighing over 1,100 pounds. Throughout the entire testing phase, engineers managed to launch anywhere from 24 to 38 of these missiles, but only 16 of them actually had a fully functional control system. Due to extremely poor test results, all work on this project had to be completely shut down in March 1945. All the freed-up resources were then urgently redirected to the production of Me-163B rocket fighters. Flying the Me-163 required a very specific set of skills. In a very short window, the pilot had to find a target, make an attack, and then, with the engine already shut down, avoid pursuit and land safely on the first attempt. The units therefore drew heavily on experienced frontline pilots, many of them with prior combat success and glider experience. Even so, the overall combat effectiveness of the Komet remained low. Time spent training and preparing for Me-163 operations also removed experienced pilots from more conventional fighter duties, where they may have been of greater practical use. The first unit to get equipped with these new Me-163 aircraft was the Erprobungskommando 16, which was formed in the spring of 1942. Command of this special unit was handed over to Oberleutnant Wolfgang Späte. He had been awarded the Knight's Cross with oak leaves for 72 aerial victories on the Eastern Front. Späte was also an experienced glider pilot, which made him a logical choice to lead a rocket aircraft unit. Given the unique nature of making dead stick landings, they generally tried to recruit Me-163 pilots, specifically from the ranks of former glider pilots. Training in the squadron began with basic glider work. First, the trainees would make a few flights in a standard Habicht glider. These training gliders were used in several wingspan configurations, starting at 45 feet, stepping down to 26, and eventually down to 20 feet. Depending on how well they did in the air, a trainee would graduate from one aircraft to the next, gradually reducing the wing area and thereby increasing landing speed. For example, on the glider with the 20-foot wingspan, the landing speed was already hitting 62 miles per hour. The next stage involved 6 flights in an empty Me-163A, which landed at speeds well over 93 miles per hour. The next phase was gliding down from an altitude of almost 4,900 feet in an Me-163A, with its tanks filled with plain water to simulate combat weight. Only after they could land consistently did the pilots move on to flights under actual rocket power. They started with 2 powered takeoffs, followed by a single flight with half-full tanks. Finally, the pilot moved on to a combat-ready Me-163B and make 2 full sorties with a completely full tank of fuel. Only after getting through this entire cycle was the pilot considered ready for actual combat intercepts. Additionally, the trainees had to endure exhausting sessions in an altitude chamber. Practice intercepts or aerial gunnery training weren't even included in the syllabus. This unusually brief training cycle had a simple explanation. Fuel was scarce, the front was deteriorating rapidly, and most of the trainees already had combat experience. The lack of a dedicated 2-seat training aircraft also made the process harder. Initially, German command planned to build an entire network of airfields for the Me-163B, hoping to throw a solid defensive screen over Germany against bomber raids coming from the west and north. But these grand plans never became a reality. By the fall of 1944, the training squadron and 2 combat squadrons were crammed into just 1 airfield at Brandis, near Leipzig. Their main job was defending the strategically vital synthetic fuel plants in Leuna. However, those targets sat at the extreme edge of the Komet's range, which made practical use very difficult. Moving the rocket planes closer to the plants was out of the question. To take off and land safely, these finicky aircraft needed an airfield with a really high-quality surface. The first real combat sorties revealed an important paradox. The Interceptor's main advantage, its very high speed, also created serious problems. They closed in on enemy bombers so fast that the German pilots simply didn't have time to aim properly and open fire. In total, the Me-163B only managed to shoot down 9 enemy bombers while losing 14 of their own unique aircraft in the process. Even more damaging was the fact that losses from routine flying accidents unrelated to enemy action were higher still. Most researchers agree that this poor combat performance came down to weak pilot training and serious technical flaws in the aircraft themselves. Trying to learn to use a new weapon accurately in the middle of a real dogfight was clearly a poor starting point, and practicing those skills during training was almost impossible because of limited time and chronic fuel shortages. In theory, pilots could have scrubbed off some speed before an attack using special air brakes. In practice, though, they just didn't use them, because the Me-163 interceptors simply didn't have a power source to operate them. Plus, if a pilot actually did hit the brakes, he might not have enough fuel left to speed back up and safely glide home to his airfield. A new twin-chamber rocket engine might have improved the situation. In that case, cruising on just 1 sustainer chamber would happen at a much lower speed, giving the pilots way more time to aim and shoot. In practice, aircraft with these upgraded engines never reached frontline service before the war ended. Wolfgang Späte, who had already made the rank of major by then, didn't fly his first combat mission until May 14, 1944. Historically, this was the first combat sortie by the Komet. Getting his coordinates over the radio from the ground, Wolfgang Späte went into a steep dive attack on a pair of American P-47 fighters flying near the test center. But at the most tense and critical moment, his Me-163's engine suddenly died. Späte was fortunate. For reasons that remain unclear, the American pilots either did not spot his bright red aircraft or did not engage it while it was effectively defenseless. He managed to restart the rocket engine and return to base. Similar attempts to intercept lone enemy reconnaissance planes also happened on May 13, 20, and 31, but none of these sorties produced any results. In the spring of 1944, German command finally put together the first fully combat-ready rocket interceptor squadron. They quickly moved this unit to a new airfield and put Hauptmann Robert Olenek in charge. The first real combat mission to intercept a reconnaissance Lightning was flown by Unteroffizier Konrad Schiebler on July 7th. But this attempt was another failure. The fuel in his rocket plane ran dry before he could even get into attack position. Over the next few weeks, this squadron, now expanded to the size of an aviation group, was redeployed to Brandis Air Base, located just west of Leipzig. The pilots of the Me-163 aircraft were assigned the task of protecting the oil refineries from heavy bomber raids. These crucial targets were located roughly 25 miles from their new airfield. On July 28th, American B-17 bombers escorted by Mustang fighters encountered these unusual aircraft for the first time. American crews estimated the speed of the unknown planes at 430 to 500 miles per hour. The first clash ended without losses on either side. The technical condition and reliability of the rocket interceptors can be seen in the numbers. At the end of July, one unit had only 4 combat-ready aircraft out of 16, while a neighboring unit had only 2 out of 5. The first combat in which the unit achieved a confirmed result came on August 16, 1944. On that day, more than 1,000 American B-17 and B-24 bombers were heading for targets in central Germany. Around 11 in the morning, the formation passed over Brandes Airfield, where 5 combat-ready rocket interceptors were on standby and were immediately scrambled. During the approach, a gunner on an American flying Fortress spotted an Me-163 rushing in for an attack just in time. The gunner opened heavy fire from a distance of nearly 3,000 feet and didn't let go of the trigger until the enemy closed right in, down to about 160 feet. He managed to score a hit. The German Me-163 caught fire, started pouring thick black smoke, and the rocket plane plunged uncontrollably toward the ground. Luckily for the German pilot, he managed to bail out. Meanwhile, the top turret gunner from another American bomber fired at a second Komet, but this time without success. However, a third rocket plane, flown by Lieutenant Hartmut Rull, managed to break through the defensive fire, attacked a heavy B-17, and successfully shot it down. The success was short-lived. Rull's tanks quickly ran dry, the aircraft lost speed, and he became vulnerable to the escorting Mustangs, which shot the fighter down. The last 2 Me-163 aircraft still managed to trade bursts of fire with the American fighters and bombers, but neither side achieved any further success. Ultimately, after this large-scale operation, the final score stood at 2-1 in favor of the Allies. On August 24th, 1,300 American B-17 and B-24 bombers passed over Brandes. In response, the Germans launched 3 pairs of Me-163 fighters, one after another. At 12:07, the commander of the first group, Schubert, attacked a B-17 near the front of the formation. The bomber was badly damaged to its left wing but remained in formation. Seeing this, Schubert quickly shifted his fire to another bomber, but this time without success. Meanwhile, his wingman was more accurate. He scored a direct hit right into the engine of another B-17. The massive aircraft immediately started smoking, rapidly lost altitude, and eventually exploded in mid-air at around 20,000 feet. The pilot of the second pair, Eisenman, was far less fortunate. He tried to set up an attack on yet another B-17, but the tail gunner of the American bomber proved to be a better shot and downed the German fighter. While this engagement was underway, Schubert managed to land, refuel, and take off a second time. By 12:12, he added to his personal score, successfully shooting down another B-17. However, the next 2 combat sorties by the Me-163 aircraft ended with nothing to show for it. By the end of August, the operational tempo of the rocket-powered Komets dropped sharply. The reason was simple and pragmatic. Allied aircraft had completely bombed out the plant in Cologne, where the special rocket fuel for these aircraft was produced. On September 10th, the Me-163 fighters tried to intercept a group of B-17 bombers again, but without success. The very next day, September 11th, a fresh batch of Me-163 airplanes arrived at the Brandes base. That same day, American crews recorded 17 high-speed interception attempts by the German rocket fighters. Each attack lasted an average of just 30 seconds. And although the Allies did lose 3 of their bombers that day, not a single one of them was shot down by a Komet. On September 28th at 11:53, 6 Me-163 aircraft scrambled for another intercept. Around 12:08, the top turret gunner of one of the B-17 bombers opened up with heavy fire on an attacking German aircraft. The fighter took serious damage, but its pilot still managed to make a crash landing, after which he was sent to the hospital with injuries. Meanwhile, another Komet fired on one of the bombers, and the German pilot later claimed a probable kill. October 7, 1944, turned out to be an especially intense day for the German base. At noon, 5 Komets took off from Brandes to meet the American aircraft. One of the pilots reported a successful hit on a B-17. Down on the ground, however, a real tragedy was unfolding. An Me-163 lost control during landing and rammed at high speed into 3 other Komets parked peacefully on the airfield. The pilot was killed in the crash. That same day also claimed the life of Ace Schubert. His rocket airplane simply exploded on takeoff. At 12:31, other Komets went in for a new attack, but this time they found themselves facing 3 American Mustang escort fighters. The Americans' fire was incredibly accurate. The pilot of one German aircraft took a hit to the head, and the fighter itself was heavily damaged. The other Komets tried to respond but achieved nothing. Right up until the end of October, the Me-163 aircraft showed almost no activity. For example, on October 9th, the Komets tried in vain to catch and shoot down a high-speed Mosquito courier airplane, delivering important mail to the Soviet Union. An aerial duel with American Mustangs on October 26th ended just as fruitlessly. Another major test came on November 2nd when American aircraft launched a large raid on the Luna industrial plants. The attacking force included 687 B-17 bombers escorted by 400 Mustangs and 30 P-38 fighters. Only 5 German Komets were available to intercept them. By this time, Allied pilots had already figured out the tactics for fighting the rocket fighters, and the results were immediate. One of the Me-163 aircraft tried to make a quick pass on a B-17, but was instantly hammered by fire from a P-51 fighter. The German Komet exploded violently right in midair. A split second before the disaster, the pilot managed to bail out of the cockpit, parachuted to safety, and made it back to base that same evening. 2 of his fellow pilots were killed in the same action. The losing streak for the German squadron didn't end there. On November 18th, during a massive Allied raid, one Me-163 was completely destroyed right on the runway, and 2 more were seriously damaged. The very next day, another Me-163 crashed during a routine training flight, landing its pilot in the hospital. The winter months brought more losses, too. On January 16, 1945, an Me-163 exploded right while landing at Lechfeld Airfield. On February 10th, one of the German pilots was killed, and the very next day, another was severely wounded in a fierce dogfight. On February 23rd, another bombing of the base wiped out at least 4 Komets before they could even get off the ground. Heading into spring, the situation remained tough. On March 2nd, 6 Komets scrambled for an intercept mission, but they never managed to find the enemy in the vast sky. The following day, the German pilots proudly reported shooting down 3 American B-17 bombers at once. And on March 7th, a pair of Me-163 rocket fighters made a surprise attack on a lone Royal Air Force Spitfire reconnaissance airplane. To save his life from the high-speed interceptors, the British pilot had to throw his aircraft into an extremely steep dive, plummeting from almost 40,000 feet down to 20,000 feet. On March 15th, the German Me-163 rocket fighters had another encounter with enemy bombers. This time, a force of 1,340 aircraft was heading for Leipzig. The American crews didn't suffer any losses, but one Me-163 was shot down in the fierce battle. Fortunately for the pilot, he managed to bail out while his fighter smashed to pieces. The very next day, over that same Leipzig, the Germans tried to intercept a Mosquito reconnaissance airplane that was photographing the aftermath of the devastating raid. The German pilots opened heavy fire on it. The British recon plane managed to escape the high-speed interceptors, but it crashed during landing. This suggests that the Me-163 aircraft may have inflicted significant damage during the intercept. On March 17th, combat flared up in the skies once again. They didn't manage to shoot down any bombers this time, but after returning to base, mechanics counted no fewer than 146 American bullet holes in the skin of one of the Komets. On March 19th, 40 German fighters took to the air to intercept a wave of 978 airplanes. Among them were the latest Me-262 and Me-163 rocket fighters. The Me-262 pilots proudly reported downing 3 B-17 heavy bombers, but the Me-163 pilots were completely unsuccessful that day. Allied forces recorded the appearance of the high-speed Me-163 aircraft late in the month, on March 24th, 30, and 31. On March 24th, one of these rocket fighters was successfully shot down. On April 9th, a pair of Me-163 aircraft scrambled to intercept 2 American P-38 fighters. During their rapid acceleration, the German pilots hit critical speeds, causing the airplanes to become unresponsive, and the pilots temporarily lost control of their aircraft. By the time they finally leveled out and regained control, the enemy was already gone, so the Komets had to return to base without making contact. On April 10th, Lieutenant Kelb claimed an aerial victory that he scored using the special Jägerfaust grenades. That same day, another Mosquito was shot down while flying at a very high altitude of around 46,000 feet. The crew had to bail out. After this attack, the Me-163 pilot became so focused on the engagement that he strayed far off course. It took him a long time to find his home airfield, though he eventually made it back safely. By mid-April, combat operations for the Komets dropped off sharply. The main culprit was a simple lack of fuel. On April 22nd, the Germans were able to gather enough fuel to fully service only 3 Me-163 fighters. Even so, they still managed to shoot down one of the 640 heavy Lancaster bombers heading out on a mission. Because of the chronic fuel shortages, much of the ground crew ended up being sent to the front lines as regular infantry. By the time Germany surrendered, the units equipped with Komets only had about 80 Me-163 aircraft and 60 trained pilots left. Overall, German historians claim that Komet pilots shot down 16 enemy aircraft, but the Allies officially confirm only 9 of those kills. By contrast, American and British fighter pilots claimed 6 victories in dogfights against the Me-163, while bomber gunners credited themselves with a few more of the rocket-powered aircraft. But the real tragedy is that far more Komets were lost in dangerous test flights and routine training than in actual combat. To give you an idea, in just one aviation unit between late May 1944 and early 1945, at least 17 of these aircraft crashed in various flight accidents. The Komet's main drawbacks remained its very short engine burn time and the difficulty of managing closure speed in combat. Experienced pilots tried to manage their closing speed on a target using an unorthodox method. They would constantly switch the engine on and off, combining that with sharp climbs and unpowered gliding. These maneuvers required great precision and were highly dangerous for the pilot. A new dual-chamber engine could have seriously improved the aircraft's maneuverability and increased its flight time. The idea was simple. The main combustion chamber would only fire during takeoff and the rapid climb, while a smaller secondary chamber would keep the airplane flying the rest of the time. This engine, the HWK-109-509A2, reached Alexander Lippisch in mid-1944. These were experimental units, and they were installed on Me-163 test aircraft. The first test flight with the new setup took place on July 6, 1944. Taking off with both chambers operating, the aircraft climbed rapidly. Between 11,800 and 16,400 feet, its climb rate reached 410 feet per second, an exceptionally high figure for the period. However, at 16,400 feet, the Komet exceeded its critical speed, forcing the pilot to shut the engine down. The fighter then entered a steep dive, and the pilot recovered only a few feet above the water. After a rough landing, ground crews found that the heavy loads had torn off the rudder. Flight data later showed a top speed of 680 miles per hour during the flight. At the same time, the Messerschmitt Design Bureau was already working on the next version of the Interceptor, the Me-163C. For this new model, they decided to keep the wing unchanged, but the fuselage had to be designed from scratch. They lengthened it noticeably, which made room for a modern pressurized cockpit with a bubble canopy, giving the pilot a much better field of view. Plus, they finally got the fuel tanks out of the cockpit, increased the overall fuel capacity, and moved the weapons from the wing straight into the fuselage. The landing gear system stayed the same, and it was unusual. The aircraft took off on a special dolly that dropped away once it left the ground, and the fighter just landed on a skid. The new twin-chamber engine, combined with the larger fuel supply, was expected to improve flight performance. They planned to kick off mass production toward the end of 1944. In fact, they only managed to build 3 prototypes, and just one of them actually took to the air. The plan was for the mass-produced airplane to be called the Me-163C. Dr. Woldemar Voigt headed up all of this design work. Parallel to this version, engineers were working on another aircraft, the Me-163D. With this version, the designers tried to address the main flaws of the earlier models. It received a larger fuselage, which allowed for a substantial increase in fuel capacity. They set up dedicated tanks for the different chemical mixtures. About 148 gallons of fuel went into the wings, with another 35 gallons right in the fuselage. For the other fuel component, they managed to fit roughly 214 gallons right behind the cockpit, plus over 130 gallons in various wing compartments. The aircraft was powered by the HWK 109-509C twin-chamber engine. A major difference from its predecessors was a proper tricycle landing gear with a nose wheel that now retracted into the fuselage. The cockpit was still pressurized, and air was fed into it by a special compressor driven by a small propeller on the nose of the airplane. The first working prototype was ready by early summer of 1944. Pilots had already started making the first test flights, not even retracting the landing gear. But right at that moment, the German aviation leadership unexpectedly decided to hand future production over to the Junkers factories. According to later accounts, Willy Messerschmitt did not object strongly to this decision since his company was already heavily committed to other projects. Over at the Junkers plants, Professor Heinrich Hertel led the design team, and the aircraft itself got a new name, the Ju-248. The designers immediately got to work overhauling the cockpit. They fitted it with a modern bubble canopy to improve visibility. On top of that, in an emergency, this canopy could be instantly jettisoned using special explosive charges. The approach to pilot protection changed too. Instead of a heavy armored cone, the engineers used several solid armor plates. The wings of the aircraft were equipped with automatic slats, which noticeably improved maneuverability. Ammunition capacity also increased. Each of the two Mk-108 cannons now carried 150 rounds. Professor Hertel had a number of other ideas for improving the fighter, but the military command was under heavy pressure to get production going, so many of his additional ideas never moved beyond the drawing board. The first prototype was put together in Dessau in early August 1944. At first, they ran glider tests. The aircraft was simply towed behind another airplane, a Ju-188 bomber. It wasn't until October that the prototype finally got its HWK 109-509C engine installed, which allowed it to start powered test flights. Right around this time, aviation officials gave the order to put the fighter into series production. But there was an unexpected twist. They ordered the airplane to be produced back under the Messerschmitt brand, giving it the designation ME-263. On top of that, military leadership insisted that the production models use a completely different engine, the BMW 708. This power plant used nitric acid as an oxidizer and put out significantly more thrust. However, the worsening situation at the front and the collapse of German industry meant series production never truly began. In the end, the aircraft was captured by Soviet forces. The Air Force at the time was facing a severe shortage of trainers, so they decided to convert one of the production Me-163B airplanes into a training version called the Me-163S. Engineers simply removed the large oxidizer tank, and in the freed-up space, they set up an instructor's cockpit, covering it with a spacious canopy. Because of these modifications, fuel capacity dropped so much that taking off under its own power was no longer possible. So, the Me-163S trainer was strictly limited to glider training for future pilots. This particular aircraft was completely finished on May 23, 1944, and successfully made its first flight just a few days later. Initially, the plan was to build a whole batch of 42 of these trainers at the Dessau plants. However, the harsh reality of the war completely ruined those plans. The production trainers were supposed to differ slightly from that initial prototype, specifically with a different canopy shape and updated radio equipment. Nobody knows exactly how many of these training airplanes were actually built in total. But there are hard facts showing that 2 or 3 fully operational examples eventually ended up in the Soviet Union, where Soviet engineers and pilots studied and tested them extensively. Overall, the Me-163 left a remarkable but ultimately dead-end mark on aviation history. It delivered astonishing speed and climb for its time, and it pushed rocket aviation farther than any operational fighter of the war. But it also showed the limits of the concept. The Komet was fast, dangerous, technically brilliant, and brutally unforgiving, both in combat and on the ground. In the end, turbojet fighters proved far more practical, far safer, and far more useful in real service. That is what makes the Komet so fascinating today. It was not the future of fighter aviation, but it was a glimpse of one possible future and a very dramatic one. If you enjoy deep dives into rare aircraft, experimental designs, and the stranger corners of aviation history, stick around for the next story. Thanks for watching.